Hello, how are you doing? My name is Walker Rowe. Today I want to talk to you about the history of modern computing. When I say modern, I mean from 1970s and the 1990s to today. I'm talking about what launched my career, what I started off doing. As people talk about the history of computers, they start centuries back or decades back. And that story I'm not as interested in because it doesn't affect what I do on a daily basis. I mean, you could say that really the first computer might have been the weaving loom. You know, the English or someone figured out how to put a card to a loom and make it weave different patterns. Now we'll look at some other ideas that some were goofy, some worked, some did not work. Probably the Chinese came up with the abacus. Not sure if it was base 10 numbers. But then Blaise Pascal, he invented a machine to do mathematics addition. Powers of 10 had little dials on it. Cranked the handle. I think it was called the Siebel line. But anyway, he did that to help his father do accounting for his business. So anyway, we will start from the 1940s, because we're going to talk, not in this video, but I talked in the last video, and I'm going to make more videos about Claude Shannon. Okay, Claude Shannon, we call him the father of information theory. But what I talked about in my last video was his work on computer circuits. He took the work of George Boole. I have Boole's book here somewhere. And he explained how you can use Boolean algebra, logic, to develop computer circuits or logic gates, which then became transistors, which were then put on silicon wafers and then became computer chips. But Claude Shannon, he also did, and here's another book, a textbook on this, information theory. Information theory introduces the ideas of entropy and information gain. This has all kinds of applications. His goal at the time was to clean up noisy telephone signals. He worked for the AT&T phone company at Bell Laboratories. But he showed, for example, that he came up with the idea of compression. He showed you could take something large, throw away most of it, and what remained was logically equivalent, mathematically equivalent. So you could get rid of most of a compressed file, and then what you ended up with was the same thing. Quite a startling result. Anyway, this book here, Information Theory, is Dr. James Stone. I think he teaches at University of Sheffield. When he wrote this, he was, where was he? University of Sheffield. I wrote some emails to him when I was trying to understand his book. He helped me out. Now, Alan Turing is best known from this Benedict Cumberbatch movie as the person who figured out the Enigma German Nazi cipher. But, if you read this book, that's only a portion of what he did. That was monumental, of course, but I'm more interested in this. I'll talk about this in another video. Turing came up, he used the word computer tape, which is interesting because there was no computer and there was no magnetic tape at the time. But he was a thinker, so in his mind he wrote out an algorithm. He basically had instructions: move right, move left, and he figured out with these steps how to represent any algebraic expression. In other words, any number. Floating point number. Floating point numbers are what we use in computers today. It's what's used in machine learning. My goodness, he did this before there was even machines. Okay, here's Microsoft's book. I'm not going to talk about Bill Gates or Steve Jobs because they've been written about too much, and what they did was launch the consumer computing revolution. And like I said, I'm here to talk about business, but also, for example, I'm going to talk about Unix and Android and Mac and the iPhone. They're all built on top of Unix. Most of this video is going to be about Unix and the SAP company. We'll talk about SAP as well. But this book here is about memory. It's about electronic circuits. And, I was surprised to find out they talk about a binary adding machine because I made my own. I made my own using Claude Shannon's ideas. Claude Shannon showed how to use logic gates to do addition. From addition, you can do subtraction. You use this clever idea called the nines complement or the ones complement to do subtraction, because basically all a computer does, even today, it's just addition and logical comparisons, like not is equal to, not equal to. That's the Microsoft's publication, official press book by Charles Petzold. Talks about those things. Now here's George Bull. This is not his original paper. He called it the law of thought. What George Bull did was he wrote down the rules for logic in terms of Boolean logic, so you could handle logical statements as algebraic statements. Now, why is that important? Well, it led to the invention of the computer circuit by Claude Shannon. But you'd say, if this, then that, or not this, not that. It led to set theories and the idea of intersections and unions. I got my degree in mathematics at the University of South Carolina, but also took a course in, they called it philosophy, but it was really logic. And it was a good idea, and I think they should teach it now to grade school kids, because not everyone's going to understand algebra. So they let university students, to fill their math requirement, take logic. And this is logic. Probably more useful for some of you who are not computer programmers, who will never A, understand, B, use algebra or geometry. I'm a tennis player. I recently used geometry to calculate exactly the advantage taller players have when they play tennis. Now here's where we are going to focus our efforts. This is Brian Kernighan's history of Unix. Okay, he was working at the Bell Laboratories, which was AT&T, the phone company, in 1969. The idea was they needed to write a multi-user operating system. There wasn't such a thing. There was no keyboard at the time. There was no screen. When you wrote a program, you put it in the IBM mainframe, it got into a queue, the program ran, and it printed as results on paper. Obviously, you can't do TikTok that way, so this was important. Everything that came after that was based on Unix. Oddly, Microsoft bought DOS from a guy named Tim Patterson. This was not a Unix-based system. Not to say it wasn't clever, he wrote it himself. Probably the greatest business deal in history. Microsoft paid $64,000 for it, and then Bill Gates turned around and licensed it to Microsoft, to IBM. One of the greatest business deals in history. Okay, the same men working together at AT&T Bell Laboratories came up with the Unix, with the C programming language. Over here somewhere I've got the, I'll put it up here, the C++ primer. I teach, since the war in Ukraine started, I've been teaching Ukrainian teenagers Python computer programming and a little bit of machine learning. But in the fall, I'm going to add C++ language. Now, C and C++ are low-level languages. That's what lets you program computer chips, program low-level stuff like, for example, something on your phone to power a chip on your phone. But it's also used for business. It's just that it's low-level, meaning like, for example, Python, which I teach now, rides on top of C, because C is fast. It's compiled, it's fast. And then C has the interface to CUDA. CUDA is what NVIDIA made to power GPUs. My channel is mainly about computer chips. We're going to get deep into CUDA and GPUs in other videos. Now, this guy here, probably the most famous thing he did was marry Ada Lovelace, who was Lord Byron's daughter. Lord Byron being one of the most famous poets. But he talked the English government into spending an awful lot of money to build this and never completed it. And it was some kind of hand crank computer, and he did his work in 1821. What was his name? The guy Vanderbilt built. A guy at MIT did an early computer to solve differential equations, and his was steam powered, and this was in the 20th century. Now, we won't get into this, but deep learning is what came from Geoffrey Hinton, Jan LeCun, and Joshua Bengui. These guys, French, British, French-Canadian, came up with the idea of neural networks and word embedding. Wow. This is what made large language models possible. They did this in the 1980s. The actual neural network was invented in the 1940s at Princeton. Now, when you say Princeton, there's a difference between Princeton University and the Princeton Advanced Institute, where Isaac Newton, where Albert Einstein and Kurt Gödel worked. So these books here, Mathematics for Machine Learning, I'm more interested in that than the actual machine learning. You know, this is the actual machine learning as it's used today. I mean, this is building agents to do chatbots and so forth. And not only is every programmer on the planet learning to do this, I don't find it as interesting as what is the math and logic, what came before it. I mean, machine learning can be used to do predictive models, do mathematical type stuff. I find that far more interesting than large language models. Don't get me wrong, large language models are quite interesting, especially the attention mechanism, which is what actually got it to work like a human, you know, quite remarkable. I use AI all day long to do things. Okay, so anyway, so we're going to get into that. We're going to talk about SAP. I haven't mentioned Hasso Plattner. I don't have one of his books. He's still kicking around. I don't think anyone's written a book about it. He's doing more than kicking around. He started some kind of institutes at Stanford University. See, he had the idea to sell UNIX-based computer systems to business. Now, he thought small business would buy this, but he was quite shocked when large businesses bought this. But what it did was, his company, SAP, he was the tech brains. I forget who his partner was. It had been doing manufacturing and accounting and order entry and inventory management for decades in Europe, called SAP R2. on the mainframe. So it had all this institutional knowledge built up. And he had the idea, like, let's not use a mainframe for this. Let's use a network of computers. So in my view, he might not have invented distributing computing system, but he put it to use. And it took off. I mean, at a time, maybe even still today, practically all the Fortune 500 businesses ran their system using SAP. So it did everything. It did human resources, it did accounting, it did inventory control, it did replenishment, and it did it for every industry because it had all this knowledge built up. It knew how to work in process and discrete manufacturers, oil companies, chemical companies. I worked, we made a fortune. We got paid in the early days. In the 1995 I started, so about 2000. Year 2000, I worked at Georgia Pacific, BMW, Eveready Battery Company, Brock & Brock Candy Company, Lucent Technologies. I think that's it. Installing SAP, we were large teams. Like at Lucent, they budgeted $300 million, and so did Georgia Pacific. And the idea was to replace all operations with the SAP system. Quite remarkable. Usually corporations have a bunch of different systems and then connect them together. But then they use this distributed systems running UNIX. So they were the first ones to do that. Not only did it, make business, I guess, run better, more efficiently, but it got UNIX pushed into the corporate world. So it's the de facto standard. And like I say now, UNIX is what powers the iPhone, the iPad, the Mac, the Android. It even works on the little cards that, it's probably in your refrigerator. Okay, so we'll move on now and talk about SAP first in detail, and then Unix and C. And this is going to be quite interesting because we will talk about Bell Laboratories and the men who found a way to raise money when there was none and built all this stuff. In the early 1990s, a slightly disheveled German computer executive, Hasso Plattner, had the idea to replace lumbering IBM mainframes that filled entire rooms and ran along corridors with a network of smaller computers. Each of these smaller, and just as important, less expensive computers would run part of a larger system. This was the first of what we now call client-server, or distributed systems. Now it's standard fare. Hasso Plattner's system did everything a company needed, and it did it with flair. Not only was it technically sexy, it made the Big Bang possible. In the quest to upgrade a business's complex computer systems, the Big Bang is quite rare because it's highly risky. The Big Bang means a company has decided to replace all their computer systems at once. This is quite different from what companies usually do, which is to change one system at a time. They could do this because SAP was the perfect marriage between engineering and business practices. Most computers then and now are built with engineering foremost in their thinking. SAPR3, Release 3, stood out because it was a well-engineered system, packed with years of business experience, garnered from R2 and its large number of installations in Europe. Soon every CIO who had been running IBM systems for decades began to throw those away and replace their old COBOL business systems with SAPABAP and do it in one big bang. This included Georgia Pacific, Colgate, Philips, Lucent, BMW, Eveready, and others. The wild success of SAP exceeded Plattner's expectation. Flying into Los Angeles, he looked down at all the small, to medium-sized companies and thought he could sell to all of them. So he was surprised when the world's biggest businesses lined up to buy this new architecture. At that time, there were almost no alternatives to the 100-year-old IBM monopoly with its large machines, some of which were so large that they were water-cooled, like a car. Then you could connect PCs and the few mini-computers in the market like Wang together over a network. But that just lets them send data from one computer to another. They still had to do all their computing in one place. What Hasso Plattner did was distribute computers in a way that the processor, storage, and memory was pushed out to each device so that the network of machines became one machine. Then it became linear extensible. If you wanted more horsepower, add one more machine. With the mainframe, you had to just build a bigger, costly machine. That by itself would have been enough to rock the computer world, but SAP did two other things that made their product unique. First, their software did everything. Before running on Plattner's distributed network, SAP R2 had been used for decades in Europe. The company and its customers and consultants had all that time to fit their highly configurable software to everything, from retailers and chemical industries to oil and gas. SAP was so flexible that you did not need to change its code to make it fit your business. Yet it still let you do that, if you needed to. But these CMODs, customer modifications, did not and could not break the core product. That appendage design was another novel idea. SAP did all the major functions a company needed: accounting, logistics, warehouse management, bill of materials, production planning, and it did it for seemingly every industry. Because it had decades of business experience, R3 brought together engineers and business people in a way that an engineering company alone could not have done. If you think of other companies at that time, like Oracle and Microsoft, their core product was software. It was up to their customers to make it do something. What SAP built was different. It was dazzling in its technical dexterity, yet it wowed the business community too. Soon, the USA was inundated with funny-sounding Europeans and Australians who had experience in configuring the many SAP screens to make it match the underlying business processes. Companies employed hundreds of these engineers and paid them like tennis pros. It was quite different from so many computer projects today because there were more business consultants than programmers. The consultants knew how to throw the many switches of the highly configurable system to make it match cash or accrual accounting systems, discrete, process, or continuous manufacturing, etc. Second, at a time when all programming was pretty much a wordy language, often derided as hopelessly tangled spaghetti code, called COBOL, the German engineers built ABAP. It was engineered like a Mercedes. It was absolutely elegant. You have to be a programmer to understand the thrill. You could look inside the running code. You can't do that with COBOL. You could stop it, change it, then let it continue on its way. The only other language at that time that allowed that was BASIC, but you could not run an entire company on BASIC. BASIC was a device for pocket calculators and PCs. And when Bill Gates and Paul Allen came along, it was pushed onto early gaming consoles and eventually the IBM PC, personal. The birth of the modern computer, UNIX. Most SAP R3 customers ran their systems on the UNIX operating system. Most people have never heard of UNIX, even though they use it every day, even today. It was built in 1969 just before the Beatles broke up, yet it endures today. It not only endures, it dominates. UNIX and its many variants and knockoffs powers everything from Apple, iOS, Macs, Facebook, Android, Google, Amazon servers, and the software that we call the Internet. What is remarkable is that the world knows almost nothing about the researchers at AT&T who built UNIX and wrote the C programming language. Practically all software today is derived from C, and the extension to C, C++. To have made either product would be remarkable. To have built both is the work of genius. It's as if these men invented not only fire, they invented water. Thus, they were responsible for creating the elements of the universe. No one has done that since, well, God. You might think that Ken Thompson and Dennis Ritchie would be well known since they won the Turing Prize in 1983. But people didn't even know who Alan Turing was until Hollywood made the movie The Imitation Game in 2014. The other men are Brian Kernighan and Doug McIlroy. They did not win the Turing Prize, but they worked side by side with Ken Thompson, who wrote UNIX, and Dennis Ritchie, who developed UNIX and C at the time SAP released SAPR 3. There had only been one computer for business, IBM. It was a genuine monopoly. People called it Big Blue. People at that time said no executive had even been fired for making the decision to use Big Blue. So Thomas Watson founded IBM in 1911 to sell his electronic tabulating machine. Its computers were called mainframes. They were big. They took up whole rooms. They were expensive, and they ran in batch mode only. You could not type commands, as they did not have a keyboard or a screen until much later. Instead, you fed it instructions using paper cards or magnetic tape, and it printed out results on paper and saved as data on magnetic tape. Those paper cards and tape were still in use well into the 1990s. To say that it was a batch machine means that it ran a program without any human pushing it along, without any kind of immediate response. Instead, the user fed it instructions, then waited for the output to come later. The programmer added the batch job to a queue. He or she gave the mainframe some instructions using JCL, job control language. Below the JCL was COBOL, or whatever code the programmer had written. You waited minutes or hours, as other computer programs ran before yours. If you made one spelling mistake, when your job was finally queued up, it came crashing down, summarily ejected without a hint of empathy for all the time you put it. The error was printed on paper, which you could retrieve by queuing up at the receiving desk of the data center. Then you had to do it all over again. There was no interactive computing at that time. We call that kind of conversation with the computer a shell. Today, when you type commands into your smartphone or tablet, the screen, which is the interface to that shell, the computer responds right away. That's interactive, or at least it appears to be. Technically, the shell submits a command, then waits for the results. But it's so fast that you aren't generally aware that several steps have taken place. Ken Thompson made it work. The IBM mainframe did not support that kind of interactive computing until it wrote something called CMS in 1964. That made possible data entry screens to which users could type information, like business data. The batch model dominated computing until personal computers, PCs, were invented. IBM introduced its first PC computer in 1981. Apple built its circuit boards in 1976. It had no keyboard or screen. It was just a card. Bill Gates and Paul Allen used a DEC, Digital Equipment Corporation, PDP machine to write basic language programming code for similar cards used by hobbyists like the Altair. Microsoft never built a computer. Instead, they purchased DOS from Tim Patterson on the cheap and in one of the most lucrative business deals in history, licensed it to IBM for their new PC, who agreed to let Microsoft sell it to other manufacturers too. Regarding the business market, there were some alternatives to the mainframe, but it was a niche market. Wang and DEC, Digital Equipment Corporation, built what were called mini computers. Dr. Wang held the patent for magnetic core memory that the IBM mainframe used, but his mini computers never could make a dent in the IBM monopoly. Wang mainly endured as a machine for word processing. The horror fiction writer Stephen King bought one to write his novels. If you leave the Lincoln Tunnel from New York City and drive west, past the endless lines of chemical tanks, pipelines, and the sprawling Newark Airport and continue west, you eventually run into the leafy green part of New Jersey in such bucolic towns as Basking Ridge, Princeton, and Murray Hill. Murray Hill is where AT&T moved its research division, Bell Laboratories, from New York City. AT&T was America's telephone monopoly from 1883 until it was broken up by the Antitrust Court in 1975. Its founder, Alexander Graham Bell, invented the telephone. Like most monopolies, it behaved like one. As late as the 1970s, you were not even allowed to own a phone. You could only rent one. AT&T invented the term long-distance phone call. In its early days, making a long-distance phone call was truly a technical breakthrough. Later, it just became a reason to charge more money. Such bullying of the consumer is what led to the invention of Skype as a way of going around long-distance charges. You could argue that AT&T, like IBM, and even Microsoft, Google, and other monopolies, stifled innovation. But there is one area where AT&T did much to foster innovation. The company spent freely to hire the best technical minds for their research division, Bell's Laboratories, now called Bell Labs. Their state goal was to solve technical problems with the phone system, like reducing static on the line or improving relays so that a call would be clear regardless of the distance. But its researchers were free to work on what they wanted. After all, you cannot tell visionaries what to do when you cannot envision what it is they might do. Bell Labs invented devices that were crucial to telephone transmission, but they also made much that was tangential to it, like the transistor and semiconductor, They vacuum tubes, which were the switches that came before those. Researchers working at Bell Labs invented the microwave, laser, and the cell phone. A couple even stumbled upon dark matter, something they thought was interference. They won the Nobel Prize for that, as it's now known as what makes up most of the universe. And Claude Shannon single-handedly invented an entire field of study known as information theory, something we will explore at length. Regarding the semiconductor, the men who built Intel left Bell Labs to turn the semiconductor to do that. And Bell Labs invented UNIX and the C programming language. AT&T worked with GE, General Electric, and MIT to create an operating system for the GEXXX system. It was to be a multi-user system called Multics, to be used on a time-sharing basis. Time-sharing is how mainframes were used at the time, rented by the hour, day, or even minute. But multi-user means more than multiple people logging in at once. It also means the ability of a single CPU to do multiple things at the same time. That's a problem that UNIX fixed. The Multics project was a costly fiasco, so AT&T walked away. But when they did so, they stranded a pocket full of engineers who were then looking for something to do. Ken Thompson et al. Then went looking for financing to carry on. But Bell Labs turned down their original proposals. So Ritchie and Thompson proposed something that would solve another problem. They said they would write software to help the patent department handle their voluminous paperwork. At the same time, they could work on their operating system. Then they found a PDP-11 for $65,000. This was at a time when there were no PCs. Even the GE computer in PDP had only a fraction of the memory that you would find on your cell phone. The PDP-11 had 24 K bytes, 40,280 of memory. The average smartphone has more than 1 million times that. The biggest cost of a computer then was memory. It was expensive because it was made of electromagnets connected by wire. That is called magnetic core memory, which had been Dr. Wang's idea. Turn on the circuit and that is a 1. Change the polarity from positive to negative and that is a 0. Leave the power on and it remembers what you have done. That is the very definition of memory. Now memory uses silicon semiconductors and costs a fraction of what it used to. Alan Turing and Claude Shannon envisioned computers using 1s and 0s to store data. The PDP-11 did that. UNIX, like Windows, Android, and Mac OS, is an operating system. That's software upon which user-facing software, like Google Chrome, sits. An operating system makes the computer do basic things, like respond to input from the keyboard, connect to the network, display output on a screen, write data to disk, and read data from memory. Ken Thompson got the key components of the UNIX system working in 3 weeks. This was during a 3-week trip his wife and kids took to see Ken's mother. It's amazing what one can do when they get away from the mother-in-law. While UNIX was built on a big for that time computer, it also runs on small ones. Although at that time, it would take more than a decade for anything to come along that you would consider small. UNIX was not open source software. Such a thing did not exist at that time. The AT&T monopoly was not about to give away its product for free, and it sued when others tried to use it anyway. But as UNIX was improved and added to over different versions, Bell Labs licensed it to several universities. The programmers wanted feedback on their product. Eventually, arguments broke out over exactly who owned UNIX and which parts had been copied from who. The University of California at Berkeley created a BSD version and gave it away. AT&T sued. Eventually, BSD won. That's all history now, as there are a plethora of Unix systems and systems that use UNIX at its core, including Apple Mac, OS X, Apple iOS, Android, and the NSA's secure Unix. Apple chose Unix for its Macintosh machines. They took the idea for a graphical screen and a mouse from Xerox and put that on top. Master salesman, engineer, and preeminent business strategist Bill Gates hurriedly bought DOS from Tim Patterson so he would have something to show IBM. It's not Unix-based. If you have used a Microsoft Windows, and who on the planet has not, you might know that you can run the CMD command to open the DOS shell. This lets you type commands directly into the screen. Before Microsoft made Windows, typing commands was the only way you could use DOS. The famous DOS C:\prompt was absolutely intimidating. You turned on your computer and a black screen appeared with a blinking cursor. gazed at you like that creepy eye of HAL in 2001: A Space Odyssey as it challenged you to do something. UNIX has graphical interfaces today, but most people who use UNIX systems for business prefer to use the character-based command prompt, as you can string together commands to do many things at once. DOS never worked like that. DOS had a small set of commands to create a directory, copy files, etc., but it mainly served as a system to run the character-based programs that quickly followed, like WordPerfect, the first word processor. Later spreadsheets, like Lotus 1, 2, 3. But the business and scientific community did not and could not run their businesses and universities on a PC then. It's a great irony then that we have come full circle and today they do precisely. The massive Amazon and Google data centers are warehouses of row after row of PCs stacked high. They use the same architecture for which DOS was built. Companies who built large computers for business have gone out of business. That has given way to what we now call commodity hardware. But the major difference is the 8080 architecture systems, originally built by Intel and the Wintel monopoly, run Unix and not DOS. About half use Windows systems, the argument over which is best rages even today. PayPal founder Elon Musk was famously fired as CEO as he wanted to run PayPal on Windows, and those who won out wanted Unix. Even in Microsoft's own data service business, Windows Azure, customers can rent Unix servers.